So good morning, everyone. Thank you, Roberta. So my name is Killian Pujol, and I'm a third-year PhD student working in Toulouse in the Laboratoire d'Aérologie, as well as in partnership with Laboratoire Sciences pour l'Environnement, which is in Corsica. And the goal of my PhD is about improving the prediction of heavy rainfall events, specifically in Corsica using neural networks. So this is the outline of my presentation. I will give a bit of context about heavy precipitation events in Corsica, as well as the scientific questions that were raised for the PhD. I will go through the results of my first work and paper of the PhD, and as well as the current work I'm doing. So a bit of context about Corsica. So given the weather that we have this week, one might think that Corsica is a dream, but sometimes the dream becomes a nightmare, as this picture is showing. So this is something that is related to the Mediterranean region in general, which can be prone to extreme weather events, which can cause significant damages and casualties, as many events can testify. And it is a densely populated area, so there is a need to better understand the physics behind those events and how can we better predict the occurrence of such events. So yeah, it's a crucial aspect for the Mediterranean region. And concerning the heavy precipitation events in Corsica, a lot of research has been done. We can cite the HIMEX program that was performed between 2010 and 2020. So here I show some results about the general context, the synoptic atmospheric context that is a precursor that precedes those events, specifically in Corsica. The general context is well known. It's the warm sea that provides the air with moist and unstable air, and orography, which is a constant around the Mediterranean and especially in Corsica, that triggers the convections. So the synoptic scale context is well known, the more local circulation as well. So all those research efforts shows that the physics behind those events is well known, and the issue is not to understand the physics, it's about predicting those events, which is still challenging, and we can cite the derecho of 2022 that happened in Corsica, but it was difficult to forecast an event like this. There is many reasons why with numerical weather prediction models there are challenges to predict such events. We can cite the high sensitivity with initial and boundary conditions, which is something that is general with the NWP models, but specifically when it comes to those events in the Mediterranean. It's difficult to represent some physical processes, such as the coupling between ocean and atmosphere, and the turbulence as well. And so the two studies I show here are specific to the Mediterranean, although it's a general issue with numerical weather models. And there is also a difficulty with increasing spatial resolution, which could help to better represent local circulations, but the computational cost would drastically increase with this. So this shows that using numerical weather prediction models is still difficult to use them to forecast those events. That's where AI comes in. So here I show some figure from the paper of Lam, which is a GraphCast that was presented this morning by Laure. And we saw that in general there are a lot of existing artificial intelligence models that can forecast weather. So this is something that exists. And when it comes to how do we do that? How do one build and perform forecast with a model like this? Which data should you use? We saw that you can use observations as well as post-processing the output of numerical models. And there is also methods that combines both approaches and that are promising. So given this context, the scientific questions for the PhD was how can AI be used to improve forecasting of intense rainfall events in Corsica. I will separate this question into 4 more specific questions. So first, how can one use AI to improve rainfall forecasts? And secondly, how can we extend those forecasting to heavy rainfall? And finally, how can we apply those forecasts to Corsica and its specific characteristic? And what can we learn from AI about the dynamics of those events again, specifically in Corsica? So I will try to tackle down those 4 questions here. And I will now talk about the first part of my PhD, and so I will just go and do this. So at the beginning of my PhD, we used a database that was provided by Météo France, which is the MétéoNet database. That covers those 2 specific regions that we can see here, what we call the Atlantic region and the Mediterranean region. Between 2016 and 2018, there was a lot of data in this database. What we used are the fields that were observed on ground stations, which we can see here by the dots. And we also used the numerical weather prediction output from the regional model AROM and ARPEJ. The difference here, so AROM is, as presented earlier, AROM is a more regional model with a finer resolution, and ARPEJ a more global one. And here we have surface fields, whereas with ARPEJ we have 3-dimensional fields with 7 isobar levels. So that's the database. And using this, we want to be able to do this forecasting task. So the model that we will develop has to, at a given weather station, forecast if the cumulated rainfall between a given point in time and delta T just after this point, if it will be lower or greater than a rainfall threshold Q. To perform this forecast, the model can use the data that is observed at the weather station, so at the present time and past time, as well as the forecast data provided by AROM and or ARPEJ. So this is what we want to perform as a forecasting task. And this is the neural network that we used. So as I said, we have 3 different types of data. We have weather station data, which are time series. We have AROM fields, which are a time series of surface fields, and ARPEJ fields, which are time series of volume, 3D fields. So for each of these data, we have 3 branches with neural networks that will help to extract the information. So weather temporal information that we have with LSTM, which were presented all throughout the week. And the same with AROM and ARPEJ, but here we have a convolutional neural network to extract the spatial information inside the data. And so we have 3 branches to extract information for the 3 different types of data. And we will study separately each of those data, as well as together, that we can concatenate. We also use constants related to the weather station at which we want to perform the forecast. So the latitude, the longitude, and the height of the weather station. Sorry. I will try to better touch that. Okay. As well as temporal information of the weather station, so the time that we want to perform the forecast, so the hour of the day and the day of the year. And precisely what we want to do is we want to be able to say if the accumulated rainfall that will come delta T after the initialization of the model, we want to be able to say if it will be greater or lower than a given rainfall threshold. In practical terms, the model will predict the probability that it will be greater. So this is a probabilistic forecast. For practical reason, we want to study a deterministic one. So we have to consider a critical probability, and we will set this critical probability and to make this deterministic forecast and say if the probability that is given by the model is greater, then we will forecast the occurrence of the event. And just for, to better understand, we call the hybrid model the model when we use the 3 branches with the 3 types of data. So that's what we use. And first, I will give an instance on what kind of forecast can we do. So this is a case study. So this is what we call a Sevenol episode. So you have wet, moist air that is coming into the Massif Central in the 7 regions that can bring a lot of rain. On the left, we have the forecast from Arom, the raw forecast from Arom, and on the right it's the hybrid model that we built. And here we are looking at the true positive in green, the true negatives in white, the false negatives in red, and the false positive in orange. So what we can see here is for this particular event, we succeeded to correct where the raw Arom forecast failed. So we can see that we have way more true positives and no false negatives. However, we have an increase in false positives, which summarize a bit the behavior of the model. And this will be discussed later. But yeah, that's what the model can give for one instance. So let's look at some statistics now. So here I will present a bit the difference of performance of the model. First, we are evaluating the model on the Pearce skill score, the PSS. So it is difficult to choose evaluation metrics. We compare different, but here I will present mainly on the Pearce skill score. It's a metric that we want to maximize at 1 being the perfect forecast. And here we compare different forecasts. So in gray here we have the raw Arom prediction. In blue we have the model with only the weather station data as input. In red only with Arom data. In green only with arpège. And in black it's the hybrid model. And we are evaluating for different accumulation window delta t between 1 and 24 hours. So what we can see is that when we only use the weather station data, the performance drastically decreases with delta t. And as soon as we use some forecasted data with, from Arom and arpège inside the model, the performance is way more stable and it's overall better, and it's outperforming the raw Arom deterministic forecast. Overall, the best performances for short and longer lead times is given by the hybrid model. So that's the first results, and that shows the complementarity between the observed and predicted data. And so this is performed for the 5% rarest events, which, as an example, is 14.1 millimeters in 24 hours, which is not that extreme. So what happens when we increase the intensity of the events that we want to predict? So here we compare the benchmark Arom, and here it's our hybrid model. And the warmer the color is, the more intense events we are trying to predict. The more intense being the 99.9 percentile, which represents for 24 hours around 100 millimeters. So what we can see is that the benchmark performance is decreasing as soon as we increased the intensity of the events to forecast. Whereas with the hybrid model, we have some performance that are more stable, and which shows that this approach can be useful and promising for the forecast of such events. So all those results were performed on the Mediterranean region of the dataset. And something that was important for our work was the discussions on the loss function and the critical probability. So we tried different loss function to see what was the best compromise, because as I guess you know, that's when you compare the performance with reality, and when one wants to predict a rare event, you have a few data in the data set to learn from. So you have to cope with that. So here we are looking at the Peirskill score and the sensitivity with the critical probability for our deterministic forecast. We compare the binary cross entropy here, so the classic loss function. It's weighted variant, the weighted binary cross entropy, which is here, and a custom loss function that we developed, especially Roberta and Jean-François in Corsica, that is made to optimize the Peirskill score. What we see is that, well, choosing a loss function is a matter of an informed choice. And when you use the binary cross entropy, you have to be really careful about which critical probability you should use. And you can reach the same performance than with the other ones when you set this critical probability with the actual frequency of the event that you want to forecast. Whereas with the other loss function, you have a more stability with a critical probability. So there is no better choice. It's just a matter of an informed choice of those loss functions. Okay, so I want to talk a bit about that, but this is the results of the same approach for the wind forecasting, and it's the same kind of results. But I will let Roberta present that later in the afternoon. But what you can see from this is that it's the same results, and the hybrid model is overall the best performing here. So what I will talk about the work I'm doing now. So given the result that we had, this is the two scientific questions that are left, and we want to understand how can we apply specifically to Corsica those forecasts, and what can we learn from the dynamics of those events. Something that we learned from our results, so here is one of the results I showed you. This showed that whether you use AROM, which represents more local circulation, or arpège, which is more synoptic scale circulation, we can reach similar performances, which was not trivial for us. And we dive more in depth into our result, and we did the feature importance with all of our feature data. And so in blue it's when we only use station, blue is station data, AROM is in red, and arpège is in green. And this is for the hybrid model. And we see that the hybrid model has a preference to use arpège data to make its forecast. This was not something trivial, and we made a more in-depth study, and we wanted to understand what are the respective contribution of those both type of data and the scale that are encoded in those data. So I first wanted to understand the synoptic scale contribution, and I spent a month in Bologna in September. The goal was to calculate what they call weather types, that's the WVT here, that are associated with heavy precipitation events in Corsica. So here I show the synoptic scale atmospheric context at 0 UTC before an extreme event, so the 0.5% most intense events. And I performed that for 390 events between 2000 and 2024. This study showed us that there are 4 weather types that are associated with those events. We have the Mediterranean depression here. So we have the anomalies of geopotential in color, and in red line it's the mean sea level pressure anomalies again. Here we have the more Atlantic depression that can bring a southwest flows on the island. We have also a Iberic depression, which can bring southeast flows, and a more high pressure, which is related to summer events with a lot of convection and thunderstorms. So these are the 4 synoptic scale contexts that precedes those events. The idea is to use this information first as inputs of our forecast. How can this information help to better forecast these events, and as well to evaluate more precisely our forecast with the model, depending on which weather types precedes an event, and see if there are some cases where we perform better or worse. So this is all a work in progress, and some results are being analyzed now. So I will dive a bit on how we go on conclusions. So again, my scientific question here is, how can neural network improve prediction of Mediterranean heavy precipitation events? So what we saw on the first part is that the hybrid model, again mixing observations and predicted data, seems to give the best results, and it's a promising way to better forecast those events. We saw that when it comes to forecasting, to do a deterministic forecast, the loss function and the critical probability is something that has to be an informed choice. And finally, the hybrid model can make accurate prediction for those events. So there are 2 papers in reviews. So mine, which is about rainfall forecast, and one from Roberta, which is about wind forecast. And some perspectives. So as I said, I want to use weather types to improve and evaluate the neural network model forecast. We also want to apply explainability method to better understand the decisions of our model. And finally, to better understand the local circulation, we want to explore forecast by using a high-resolution database, and I have 2 more slides about that. So we want to build, we did build a high-resolution database. The idea would be to have a more precise data set, finer data set, to better represent local circulation and understand the contribution of this circulation to our forecast. So this database is available at 1,000 meters and 500 meters resolutions, with a year of data for both resolutions. And here what I show is 5 events on Corsica that we used to establish the configuration of Meso-NH, which was the model that we used to make this database. 5 events that were which were triggered with different kind of atmospheric circulation. And so the other data that I wanted to talk about, but Jean-Baptiste did yesterday, it's the lightning mapping array SITA, which is deployed in Corsica and make 3-dimensional observation of lightning, and which is an interesting database because, well, lightning are correlated with convections, so it could be a good set of data to try and use those observations to forecast heavy precipitation events on Corsica. So that's it for me, and I'll be happy to answer any questions.